Hello, good friends. Today, we're going to unpack the important topic of large language models and the intriguing phenomenon known as hallucinations. Our discussion is inspired by the enlightening research paper titled On the Intrinsic Representation of LLM Hallucinations, a collaborative effort from the brilliant minds at Technion, Google Research, and Apple. Now, when we talk about large language models, or LLMs, we're referring to those sophisticated AI systems that power everything from virtual assistants to content generators. These models have made incredible strides in understanding and producing human-like text. However, they aren't without their quirks. One such quirk is the tendency to produce what's affectionately termed as hallucinations, factual inaccuracies, biases, and reasoning errors that can sometimes lead these models astray. The research we're delving into today sheds light on a fascinating aspect of LLMs, their internal representations. You see, while these models are often criticized for their errors, this study reveals that there's a wealth of information encoded within their very structures about the truthfulness of their outputs. In essence, LLMs might know more than they outwardly display. One of the standout findings from the study is the localization of truthfulness information within specific tokens. Imagine you're asking an LLM, "What is the capital of Connecticut?" And it responds, "The capital of Connecticut is Hartford, an iconic city." The word Hartford here is not just any token, it's a critical piece of the puzzle. The researchers discovered that truthfulness signals are highly concentrated in these exact answer tokens. By focusing on these key tokens, they significantly enhanced the performance of error detection mechanisms. In fact, incorporating exact answer tokens improved error detection across nearly all tested datasets, highlighting the precision of this approach. But here's where it gets even more interesting. Despite this localized encoding of truthfulness, the study found that error detection methods based on these internal representations struggled to generalize across different datasets. This suggests that the encoding of truthfulness isn't a one-size-fits-all mechanism, but rather varies depending on the context and the specific task at hand. It's a nuanced, multifaceted encoding that challenges previous notions of a universal truthfulness signal within LLMs. Digging deeper, the researchers explored the types of errors these models are prone to. By categorizing errors into various types, such as consistently correct answers, consistently incorrect ones, and those that vary between instances, they were able to predict the kinds of mistakes an LLM might make based on its internal representations. This predictive capability is a game changer. It means that we can potentially develop targeted strategies to mitigate specific types of errors, making LLMs more reliable and trustworthy in real-world applications. A particularly striking revelation from the study is the discrepancy between what LLMs internally encode and what they outwardly generate. In some cases, the model's internal state correctly identifies the right answer, but due to the way these models prioritize generating likely tokens, they still output an incorrect response. This misalignment points to inherent limitations in how LLMs balance likelihood with factual accuracy. It's as if the model knows the right answer, but chooses a different path when generating responses, leading to those pesky hallucinations. To quantify these insights, the researchers employed a range of methods, including probing classifiers trained on internal representations to predict output accuracy. They measured performance using the area under the ROC curve, a robust metric that balances sensitivity and specificity. The results were compelling. Probing techniques outperformed traditional uncertainty-based methods, underscoring the value of tapping into the model's internal knowledge. Moreover, the study's taxonomy of errors revealed that nearly all errors in certain datasets fell into well-defined categories, providing a structured way to understand and address them. For instance, errors ranged from outright refusals to answer questions to generating a myriad of incorrect responses. By mapping these patterns back to the internal states of the LLMs, the researchers laid the groundwork for more sophisticated error analysis and mitigation strategies. In practical terms, these findings open up new avenues for enhancing the reliability of LLMs. By leveraging the rich, albeit complex, internal representations of truthfulness, developers can create more effective error detection systems. This is especially pertinent as LLMs become increasingly integrated into critical applications where accuracy is paramount. However, it's important to note that while these internal signals offer promising leads, their effectiveness is somewhat constrained by the diversity of tasks and datasets. Truthfulness encoding appears to be highly context-dependent, necessitating tailored approaches for different applications. This underscores the need for ongoing research to refine these techniques and explore how they can be adapted to a broader range of scenarios. In conclusion, the study LLM Know More Than They Show on the intrinsic representation of LLM hallucinations provides profound insights into the hidden workings of large language models. By uncovering the intricate ways in which these models encode truthfulness, the research not only enhances our understanding of their limitations, but also paves the way for more nuanced and effective strategies to mitigate errors. As we continue to harness the power of LLMs, such foundational knowledge will be crucial in ensuring that these technologies serve us with the accuracy and reliability we demand. Thank you for joining me today in exploring this captivating intersection of artificial intelligence and cognitive science. Until next time, keep questioning, keep learning, and stay curious.